Well, good morning, and thank you very much to Ruth, to Neil, to the LBMA for the invitation. It's a distinct pleasure to be here with you and try to convey a little bit about the theory and practice of sampling. Ruth mentioned that things really heat up when there is a problem, but it's always at the back end of the issue. One of the problems that consistently show up is if the sampling was not representative, there is an unnecessary inflation of uncertainty in our measurements. It's unavoidable. No matter how good we are at the analytical métier, if the sampling that precedes it is not up to the standards, if it's not representative, we have a too large uncertainty, and that is, of course, to everybody's dismay. So let me try Mission Impossible in about 39 minutes to give you an overview of the theory of sampling. Obviously, it's Mission Impossible, as I said, so I will just give you a few insights of the basic principles from which we can all make an inquiry into what does it mean to have a sampling problem and how can it be solved. I asked Neil, since I haven't worked with precious metals very much, I've worked with pretty much everything else. I'm a geologist of training, but worked all over the process industry. And this is wonderful to come here to the precious metal thing. I said, send me some stuff I can read so I can get acquainted with the subject matter. And he sent me the Amira P754 project 2001 paper, and I read that with great interest. Of course, zooming in on what does it say about sampling. So it's all about metal accounting in this document, from mine to product. Aha, the whole pathway from mine to product. That's good to know, because that's exactly the subject matter of the theory and practice of sampling. We want to produce credible figures of metal quantities. I can go along with that. Major point of the conclusions was there. You can feast your eyes on that, while I point out that there was a demand, at least some knowledge of the errors associated with each measurement, including sampling and assaying, is essential. But it's just up my alley, so we have a common ground here. I was happy to get this background. So this keynote lecture will focus exclusively on the sampling issues involved in the work you're doing. I was happy to meet a gentleman today from an earlier lecture, which I have stolen with permission. I got the permission 15 minutes ago, so I'm happy to say that. An illustration from the 2015 conference. It's generally assumed that the metal is well mixed due to stirring caused by electromagnetic fields in induction furnaces. This is, of course, a critical assumption, crucial assumption. Is it true? To what degree is it absolutely true? Because if there are impurities there, are they completely uniformly distributed when we tap out the melt? That is the answer at the very end of the pathway from mine to product. So without in any way casting doubt on anything, how well is this verified at this end of the pathway? I hope, I trust, I'm sure it has been verified, because that is the very job you are doing. It's good to see some information on that. I would like to look that up one day. But we have many other things to talk about today that comes before this last stage. The same paper noted that to avoid the uncertainty related to systematic errors by proper process concept and appropriate sampling, when inhomogeneity of the sample material can be presumed. So heterogeneity is recognized, it is acknowledged even at the late stage. And we also know, if we go to the other end of that pathway, all the world's precious metals do not crop out of the ground as material ready for the crucible. There is a huge process going on, from ore mining, ore, broken ore, mass reduction, sampling. There is an order of magnitude gap here from 1 million to 1 billion mass per mass. Sampling is really nothing but representative mass reduction. So the mass reduction step is crucial. We need to know about it and how we can work up against heterogeneities at all scales. That's the job of the sampling part. Is there an authoritative manual or a standard or a good laboratory practice guiding document for this? Well, we all know that is scarce on the market. So it would be nice if we could get access to an international standard that tells us how we should conduct this sampling. And in fact, there is now such a standard, which is one of the messages of today. But let's just first make a cursory look. Here's 55 ton of material manually grab sampled. Will this give a representative sample? It will not. No matter how well thought out the process is, I have to say it will not. Grab sampling will not work in these tonnages at these concentration levels we're talking about. That is an important lesson, not always acknowledged. Let's illustrate what we are up against. And I want to do something today that seems really daring. I will give you very few examples from the precious metals, but I'll give you a lot of examples that deal with the same issue as we are looking at in the precious metals, mainly because I'm not at liberty to show examples from the audits and stuff I've done in this business. But it really doesn't matter, because what we are focusing on is the heterogeneity of the material and how we can sample going up against counteracting the effects of the heterogeneity. That's the job of sampling. So it doesn't matter if it's household refuse, we want to sample that because we want to find out when we burn off a ton of that, how much dioxin are we emitting to the atmosphere. That's a terribly complex sampling job, but it's crucially important for public health. And we're up against heterogeneity of this kind. I mean, rhetorically, how would you take a 1 kilo sample of this material and call it representative? That's a tough job. There are ways to do it, though, and we'll talk about them. Just to put a fine point on it, the heterogeneity is also present in many other materials and commodities. And I even found one that relates to what we are doing. So the question is, how big should the primary sample be in order for that to be representative? And then we have the job of mass reducing that down to whatever is needed for the analytical determination in the end. Series of steps. Now, how big should the sample be in order to be representative? It just happens to be apparently a good question, but it is actually the wrong question at the wrong time, at the wrong place. But other than that, it's a good question. It's not how big it should be, it is how can we make the sample representative. That is the true question. And then it has to be whatever mass that determines. Billions of standards and guiding documents start out by fixing the size of the sample without having it based on anything empirical, like, for example, a pilot heterogeneity determination assessment or something similar, which means that we are just following on a tradition. A sample has to be a certain size. Now let's try and make it as good as we can. That can only, at the best of cases, be fit for purpose. It is not representative. We have to go another way around, which we'll talk about in a moment. So actually, quite paradoxically, sampling is not so much material dependent as it would seem, because materials are so different. It is much more up against the heterogeneity. And here is a little sneak preview. Heterogeneity is a feature we can deal with in a universal manner. We can kind of look away from the material nature and only look at its heterogeneity when we are talking about sampling. In very many, nearly all cases, sampling is not a one-shot operation where you can go to the material and take out an analytical mass, knowing for some reason that you worked hard to establish that this one small sample is representative of the whole lot. It is a multi-stage process, another lesson to take home. Here I've just drawn out 3 stages in the sampling before the analysis can take place. And the principle we're going to talk about today spans the whole pathway from the primary sampling of the primary ore, lot, commodity, whatever it is, where we are, towards the analysis of the test portion. Spans could be we are interested in improving the secondary sampling or the tertiary sampling, or we could go directly to the aliquot taken out for analysis. At all these places, sampling errors abound, and our job is to eliminate those sampling errors that can be eliminated and reduce the others that are always with us. That's our job. So we can go about this in a very systematic fashion. Before we get to the interesting part, which of course mostly interesting for you, the analytical part, and I am dying to hear these 2 days about the state of the art of the analytical work that is being done here. I really look forward to that. Now, this keynote turned out to be a very timely event, since we actually now have an international standard. 2013 saw the publication of the world's first universal standard for representative sampling, called horizontal standard. In there are described the general principles needed to do representative sampling, pretty much of all types of material, at all scales, for all purposes, but usually the purpose is analysis, of course. This is good stuff, but how well is this known? The horizontal nature means that we are deliberately talking about what crosses the boundaries between different kinds of material, only focusing on the heterogeneity. The first thought is, if you haven't thought about this before, this must be complex, with all the different kinds of material, even within the precious metal sector alone. But the theory of sampling to the fore to help us there. Here is a sneak preview. DS 377, representative sampling, horizontal standard. I had the privilege of chairing the working group, working out this document. It took 5 years until everybody involved, industry, regulating authorities, scientists, agreed unanimously to this 42-page standard. And I have given you the first 9 pages in the handout here. That's what's allowed for free. And you know, any standard in the world has to be bought from the authority that is issuing it. But it's not the money that should detract you from getting this. In fact, there's nothing in the world that should detract you from getting this, and make yourself informed about the general principles that I will give a little overview of today. The general principles are 10, and that's all we need to tackle any sampling objective at any material, at any scale. Grouped into 6 governing principles and 4 sampling unit operations, more of which in a couple of minutes. But a fundamental insight where we could start is that any sampling process is never a one-shot operation. It is a multi-stage. There is a primary sampling involved, and after that we could call the rest representative mass reduction until we have the mass needed for analysis. That mass reduction is also a series of sampling operations taking place at smaller and smaller scales. That's the systematics of it. That helps us, it empowers us to look at all materials from this systematic point of view, and then just draw it down on the concrete problem in front of us. You should remember, though, that in the end, no analytical result is better than being bracketed by the accumulated uncertainty from all these steps. That's why each of these steps should be treated as a singular sampling operation. Our job is to make that singular sampling operation representative. And then we can go to the next stage and make that representative. Luckily, there's no interaction between stages, so we can defocus the complex problem into a series of individual sampling operations governed by the same principles, using the same sampling unit operations. I hope it's already beginning to sound a little more manageable. The primary sampling, let's just say for this discussion that it has an uncertainty of 5%. There. Which is ridiculously low for real-world work, but let's just have it for an argument. Let's say that the mass reduction steps in the laboratory amounts to 2% and that the analytical error is 1%. These are just figures for interest for the discussion. Error propagation makes that 5.5% in total. What have we learned here? The total uncertainty is dominated by the primary sampling uncertainty. Let's take an example from the other side of the spectrum, where we really have a very serious primary sampling issue. Let's say that the uncertainties at present are 55%. And let's also say, for the sake of argument, that we have problems in the laboratory. Mass reduction, subsampling, 35%. We are still, of course, as a nod to this audience, we are still, of course, in complete command of the analytical work. Error propagation at work here, 65%. What do we learn here? Again, the primary sampling dominates the total uncertainty budget. But also, we certainly need to do something about what we have discovered of issues in the laboratory. Just a fine point here that what comes before analysis is often overwhelmingly larger in the total error budget, unless or until we have managed that uncertainty risk. Theory of sampling tells us what to do in these cases. Ladies and gentlemen, the arch enemy, heterogeneity. It's a cartoon, but it gives the essence of what we're up against. Let's take one sample. Let's say we hope we can take just one sample. It might be this one. Let's say that the black spheres here is the analyte, and the white sphere here is the matrix, the filler, the gang, what have you. This sample would have 75% of the analyte. A pretty high estimate of the total average concentration in this lot that we can clearly see is way wrong. Causes for concern. Let's take another sample to see what we're up against. 25%. Let's take another sample. 0%. Now we are in deep trouble. Fingers are usually pointed to the laboratory, absolutely without any reason. This is a fundamental sampling error at work when we have low concentrations. If we take one sample or a few that are too small to do the job. Another lesson learned, we need to do different from grab sampling in the primary sampling state. We must do composite sampling, structured so to face the problem that we are facing. Heterogeneity doesn't have to look like this. It can also be structured. Here is the most important example of what structured heterogeneity means, some sort of gravity segregation at work. I'm sure we're all aware of that. And the same thing that happens if we take gram samples or too few, too small to make a composite sample. Now, the primary sampling stage is where it's most critical, so that's where we have to work real diligently to get everything under control. We can do it. The theory of sampling will show us what to do, but I've already mentioned composite sampling. That is the door opener. I have to say that one good thing about this little bit of drama here, despair, is this takes place at whatever scale you're working. It's the same issue, and therefore the solution is the same. It's just playing out its role in a different, smaller scale. Well, this makes it easier. Now we're already on the way towards solutions. If you can do it at one scale, you can do it at all scales, right? I just want to give you the last illustration of heterogeneity as concentration of the impurity, for example, goes down. No impurity that you are interested in are in these concentrations. I know it's much lower, but the principle applies just the same. As you can see, the distributional heterogeneity, the spatial heterogeneity gets really troublesome as the average concentration goes down. But you could argue many times we don't want these problems. We melt the whole thing, and then we have a well-stirred and well-mixed melt, and from there we can go on with your work. And you're right, but of course we can't do that necessarily all the time with all the tonnages we are processing. And what if we have to characterize what comes to the door of the refinery? We don't usually melt all of that just to get an idea of the concentration. So we have to work smartly, as many of you do already. You pay a percentage up front and then you close the deal later when you've got some of this material in a melted form and much better under control. But what happened with the mass reduction that took place from the delivery to that's little parts, some of the material that we can control much better. That's where we play out this game of sampling as well. I just want to point out that sometimes the heterogeneity is a function of the way the material was laid up. Now we need to know about these things so we can design sampling operations, sampling procedures that actually face up against the structured heterogeneity present in the given situation. It's not so, I'm afraid I have to say, that a random sampling backed with classical statistics will solve everything. It's unfortunately not so when we are up against spatial heterogeneity. There are two aspects of heterogeneity: compositional, which is intuitively clear what it means. Well, we've seen some illustrations of that. And then there is the aspect of distributional heterogeneity. That's the real killer. That's the real enemy we are up against. But structured composite sampling pattern on the problem at hand will solve that problem. An example of what I have seen from another sector of industry than you're working in. It's not always you can see heterogeneity with your eyes. That is only making the world a little more challenging and complex. So this looks kind of, we wouldn't say homogeneous, we would say kind of uniform composition. There are no such thing as a homogeneous material within science, technology, and industry. A perfect crystal would be close to it, but that's really not much interest for us. All materials we are dealing with are heterogeneous to some degree. It is only a matter of to which degree. Now, the good thing is the theory of sampling posits these general principles and unit operations, and they can work on any degree of heterogeneity. Picture yourself being 15, 16, 18 years, trying to learn to drive a car. You go on some learning circuit, or in some countries you learn by having an instructor by you, and you go out in real traffic to learn. But you don't start downtown and metropolis at 350. You don't start trying to learn to drive a car there. You take a long stretch of 10 kilometers and try to learn there. It's a little bit the same here with a kind of twisted analogy. If we can deal with the most difficult heterogeneity, and we have to learn what to do. If we can deal with that, we can then deal with any type of material that happens to be less heterogeneous. There's no switch in operation. There's no change of procedures. That's enabling us to tackle a large set of difficult issues. What he's doing here is taking a spear sample, but and that is usually then put into the bucket, and then it's usually considered a reasonable primary sample, or maybe an increment together with others. And there's a hidden problem here that will disqualify this forever. That is, you don't get to the bottom or to the center of the lot in this case. It's trivial, but it's very often not acknowledged. There is a thing in the theory of sampling we call the fundamental sampling principle, and it simply says all increments, all small samples that are maybe going to be put together, must have the same probability of ending up in the sample, i.e. you must be able to reach everywhere physically, geometrically in the lot of material. If you cannot do that, all bets are off. We still get a fantastic analytical result in the end with 4 or 5 decimals, precision, but the accuracy with respect to the lot that we want to characterize with this enormous precision is void. Representativity demands that the fundamental sampling principle is honored. But we just have to know that and organize our sampling procedures so we can do it. The consequence of not doing it is a breach of due diligence with respect to sampling representativity, and that plays into your analytical uncertainty, which blows up. Nobody wants that, I hope. So we just have to do something to do it right with big piles. I just took one example with a company that did allow me to show a few things. You have to go all the way to the bottom of the pile with your increments. It's a trivial geometrical case, but the principle is very easy to apply to other situations, those that you have in your head right now while we're talking about this. So let's go to the other end of the scale here, sampling in the laboratory. What is the difference with respect to the field, the plant? Only the scale. sampling, ladies and gentlemen, representative sampling, is scale invariant. Now it's beginning to be easy. We just have to learn these principles and then we're off. But we will win at the end of the race course. Now, we've actually talked about 2 of the 6 governing principles with these few examples. There is not time to go into the number 3, 4, 5, and 6, although I will mention 6 a little bit later. But that's all there is. I would like to present to you a giant of science who very sadly died last year. Actually, November 15. Pierre G. I am sure many of you have heard his name if you have just been a little bit interested in sampling. Pierre G. single-handedly developed the theory of sampling in a bout of energy from 1950 to 1975. He's written 9 books, given 250 invited speeches. He's done a lot of stuff. He's never worked at a university. He's been a consultant nearly all his life. Imagine doing this complex development of a theoretical, heavily based on mathematics and statistics at that time, all alone. That's really an intellectual achievement. His major breakthrough was that he identified 7 sampling errors that cover everything that can go wrong with sampling, and then meticulously worked out how to avoid these errors as much as possible. It's a huge job. On the way, he did 2 PhDs, one in minerals processing and one in statistics, in order to solve that problem. But we are not going to talk about all the complexity. It's only about 15 professors in the world who have read the whole of his work, and it's deep. But it can be made very accessible, and that's my job here today. The overview is there are 7 sampling errors, approximately, from 3 sources: the material, the sampling process itself, and also if the lot happens to be moving, if we are sampling a process, a conveyor belt, or what a pipeline, what have you, then there are 2 minor sampling errors are cropping up there as well. That's the only sources of errors. They're grouped into 2 groups. One is called the correct sampling errors, and that usually causes a lot of frowns. What is a correct error? It's actually a consequence of what's easy to understand. What is an incorrect sampling error? These are the bad guys. They produce a sampling bias that are really haunting us. The job is to get rid of the incorrect sampling errors. If and when we have done that, what are we left with? The correct sampling errors. When sampling is correct, that's because we have done away with the incorrect sampling errors. So there's no mystery in these strange names. But by playing around with this understanding, we can analyze a sampling situation, however complex it is, however complex the heterogeneity, and the physical conditions under which we have to sample it. That's the elements of the theory. One of the 9 books has reached out quite a lot, sampling for analytical purposes, 1999, translated from the French to English. But it's still difficult to get into, I must admit. So if any of you have tried, you can raise your hand. Hello, sir, let's meet in the bar afterwards and exchange notes. It's not easy. So my humble contribution to the theory of sampling is to put this into an axiomatic footing and put it into a standard that is now available to all of us. And in there, the whole thing is axiomatically grouped into 6 governing principles and 4 unit operations. I will not, in the interest of time, I will not go into giving a lot of examples of them, but I will mention those sampling units because they are the only things we have in our little doctor's kit when we are called out. Have to solve an illness that has arrived, a sampling problem. We open our little doctor's bag, and there are only 4 instruments in there. Composite sampling, comminution, crushing, mixing or blending, and mass reduction, but not any mass reduction. It must be strictly representative mass reduction. Otherwise, of course, the chain loses its integrity. That's all. We only have 4 operations. We play around with them, and that's it. That's how we solve the practical problems. It's not rocket science. We've all heard about crushing, mixing, blending, subsampling, etc., etc. That's all we do, but we have to do it just the right way, and it's really not that difficult. An analogy that goes way off the mark, but it is an analogy anyway. Maxwell's equations, we all know they summarize electromagnetics. And they describe how electromagnetic fields propagate, interact, and influence each other. When we studied physics, this was really a great summary, helps us to understand a lot of things. With all due respect, I am not Maxwell. But here is the analogy. We have the 6 governing principles and the 4 unit operations. The governing principles describe how to conduct representative sampling of heterogeneous materials, and there are only 4 agents at our disposition. They are not all involved in any particular sampling operation, but they're used when and how, and the problem, when it's analyzed, probably suggests which ones to invoke. There's no big mystery here. Actually, reasonably easy to do, with a little bit of work putting yourself into it. We talked about this. It is a multi-stage thing. Representative mass reduction is a thing that is usually in the hands of analytical chemists, or if not, it's just something we do. There are some equipment ready for us to do splitting, subsampling, whatever have you. It's interesting to go into that and find out which follows these rules or which do not. In fact, all of these do not. And I won't go into any details about what takes place in the laboratory. It is relatively easy to get the laboratory shaped up with respect to subsampling mass reduction. And there is one piece of literature, that the reference of which I have given you in the handouts, if you're interested. And that's what governs how we audit the laboratory from these principles' point of view. Now I have come to the most important impact of today. We all work hard, we know of and work with measurement uncertainty, characterizing our analytical methods. I have shown here a fishbone diagram that is representing any of the many analytical methods in use today, of which many of you are experts. I wouldn't even dream of going into it, but we can get anything and everything under control following the principles of measurement uncertainty. There is one part of the fishbone that is usually left out, however, when we do the measurement uncertainty calculations, and that's the sampling errors. How often have I not seen in the literature? It is assumed that gross sampling errors have been avoided, are eliminated. They are not part of this characterization, the measurement uncertainty. That's a problem, because in nearly every case that I know of, and many others, the sampling errors, even the irreproducible residuum of the sampling errors left, are larger, and many times much larger than the total analytical error. So there is a problem that we should just simply face up to, seriously acknowledge it, and then work the problem and get the sampling errors under control as well. The theory of sampling works on the sampling issues and delivers then the best possible representative sample upon which we carry out the analytical determination. So there's 2 elements to the total measurement error, total, including the sampling issues, the sampling errors. And if I should give an overview of how that ties in with the analytical measurement uncertainty schemata, there are 3 arrows here. One is only invoked when we are sampling moving targets. The other ones are here, the incorrect sampling errors. Here they are again, the funny named guys, and the correct sampling errors here. The job of any sampling resolution is the following. Get rid of the incorrect sampling errors. They produce a sampling bias. I'm going to talk about the sampling bias immediately after this. There is a very interesting surprise about the sampling bias when our experience are from analytical methods, where we have an analytical bias, an analytical imprecision, or precision if you like, and we can work both, and we can correct for the analytical bias. This is not so when it comes to sampling errors, sampling processes, and that must be new to very many here. We all know the difference between accuracy and precision. We need both of these to qualify an analytical process, for example. Illustrated here is a perfect analytical process. It is unbiased and it is precise. Bon groupage. We can also have this situation over here where we still have very high precision of the analytical method, but there is a bias. Now, under the statistical assumption that this bias is constant for the analytical process investigated, it is possible to make a correction, subtract the estimated magnitude of the bias, and then this situation transforms into this, and we are all happy, and that's what we're doing all the time. Now, switch to a sampling process. Let's say we do a replication of the sampling, the whole sampling process, including the analytical thing, 10 times to find out where are we. That is also a pilot heterogeneity characterization, ladies and gentlemen. Let's do that. And let's say the 10 results distribute themselves like this area ending there. It's not really amenable to any statistical correction. We are not really sure what goes on here. This is very surprising. So we try it again to see what goes on. Maybe we get new insight from trying again. You probably already have guessed how this is going to play out. They are now distributed there. If you did it one more time, they're distributed there. The conclusion that is reached by the theory of sampling is frightening, but it is also an opening door into how we can do representative sampling. We just have to acknowledge that as it comes to a sampling process, the bias is inconstant. Quite the opposite of the analytical bias. It is inconstant. It changes its magnitude every time we try to estimate it. Why? Because we are taking out a little bit of the material that is significantly heterogeneous, and we are definitely going to take out 10 smaller bits the second time we try out. So we are getting our hands on different parts of significantly heterogeneous material. Therefore, the analytical results will not be the same, and we'll wake up. And unfortunately, 2 minutes remaining, unfortunately, here comes the crunch. This cannot be modeled by classical statistics or a normal distribution, not even by a long-haired advanced distribution, unfortunately. So the lot is, because of its distributional heterogeneity, is not a collection of analytical results, which we can throw classical statistics at, as we do with analytical uncertainties proper, isolated. When we take into account the sampling effects, we have to work in a different way. However, it is easy what we have to do. The conclusion to this troubling understanding is simply that we have to eliminate the incorrect sampling errors, as indicated before. And that's the major first part in any small introduction to the theory of sampling. Get rid of those sampling errors that produces this sampling bias, because it is crippling us forever and there's nothing we can do. Now, the theory of sampling treats all this from a systematic point of view, the one I have illustrated today. There are a few other elements to it, but that is all there is to it. At a PhD level, it takes 4 days to get into this. Dedicated course activities for companies with brilliant minds, 3-4 days. This is then under control. So this is not impossible. It's a systematic way of thinking that has as its impact the heterogeneity and how to counteract it when we do sampling. And we owe that to the analytical brilliance and competence present here, we owe to produce the most representative samples for analysis. I hope I've been able to give you an idea of what goes on with the theory of sampling. I have added quite a lot of stuff to your handout in case you should be interested in reading more about it, and I am delighted to be here the next 2 days, all with and for you. So anybody who would like to discuss more, we will find some time. Thank you for your attention.